We will continue with another lesson dealing with exponential and logarithmic functions. In this case, the focus will be on logarithmic functions. This will be lesson 2.4. So let's look at the definition. There's a logarithmic function to the base a, and here a has to be positive. A cannot equal to 1. It's denoted by y equal log, and this is read log of x to base a, and it's defined by, again, y equal log of x to base a if and only if x is equal to a to the y. So basically this is telling you that a logarithm is an exponent. It's the exponent that you have to take this base to, this base a, to get the number x. Okay? And because of the fact that x has to equal to a to the y and a is positive, then x has to be positive. So I have in parentheses here, x has to be a positive number. Now the domain of your log function will be from 0 to infinity, not including the 0. Okay, x has to be positive. The domain will be from negative infinity, or the range I should say will be from negative infinity to infinity. The x-intercept will be at 1, 0, and the vertical asymptote will be x equal to 0. Okay, so let's look at a few examples where you use your calculator. Now on your standard calculators, whether it's a graphing or just a scientific calculator, you're going to have the log key right here, which is computing the logarithm to base 10. And the calculator will also have an ln function, and this is log to base e. So if there's no base indicated, we have log of x to base a. If there's no base indicated, that's always understood to be base 10. Otherwise you have to put it in base 2, base 3, whatever. If it's just ln, that's understood to be base e. So if I want to compute the log of 75, I hit the log function, type in the 75, close the parentheses, I hit enter. So the log of 75 to base 10, again the base is understood is to two places, 1.88. Clear. If I hit ln and type any number, say 55, hit enter, then this says the natural log, or the log of 55 to base e, is to two places, 4.01. Okay. So if I want to compute, say, the log of, say, 16. Okay, and say I want base 2. Well, your calculator will have you can compute, on your calculator you can compute the log to base 10 into base e. So if you have some other base, you'll have to use a change of base formula that'll come up later on in another lesson. But in some problems like this, you don't need a calculator. Here's the log of 16 to base 2. Is equal to what number? Well, again, because the logarithm is an exponent, here's your base 2. So basically we're asking 2 to what power is 16? Well, it's 4. 2 to the 4th is 16. So that's your logarithm. If I want to find the log of, say, 1,000, again, this one I can do without the calculator, because the base here is understood to be 10, so all we're asking is 10 to what power is 1,000? Well, it's 3. Okay, so that's it. That's how you can get the base, or the logarithm rather, to problems like this where you can get an exact answer. Otherwise, if it's not an exact answer, you can use a calculator. Now, getting back to the graph that I have here. The logarithmic function, and this again, or the graph of the logarithmic function, so y equal log of x to base a. If the base is larger than 1, then like I have over here on the side, the vertical asymptote is going to be x equals 0. So the graph is going to approach this asymptote. It's going to pass through this point right here, because the log of 1, so if I put a 1 where the x is, the log of 1 to any base is going to be 0, because any value to the 0 power is 1 other than 0. So 2 to the 0 is 1, 3 to the 0 is 1, 10 to the 0 is 1. Okay, so this point right here that I have where the graph crosses the x-axis is the x-intercept, which is 1, 0. Okay. Domain is, again, all positive numbers. The range is -infinity to infinity. And just so you get a better idea as to what the graph looks like, this right here is the graph. Y equal log of x to base 10. Okay. Now notice what happens to the graph if I change the base. Okay, so I'm going to decrease the base. Okay, so there's base 9, 8.8 there. Okay, there's 7.4. There's base 6. Notice what the graph is doing as the base decreases. Okay, there I have a base of 3. Log of x to base 3. If the base is 1, it's not defined. Okay, so at 1, notice there's no graph. It's not defined. Now, if the base is between 0 and 1, okay, the base is between 0 and 1, notice what the graph does. So here it's 0.2. Okay, it still passes through 1, 0 right here. It still passes through 1, 0. It still has a asymptote of x equals 0, which is the y-axis, and then it goes down. As you can see, it's decreasing. When the base is larger than 1, the graph is passing through 1, 0 and is going up like this. Okay. If the base is between 0 and 1, that is less than 1, then it's coming down this way. Okay. So that's what the graph looks like. The domain and the range are still the same. That doesn't change. So for this one, the graph of y equal log x to base a, where a is less than 1, is going to come down this way. Okay, so if I draw it here, it's going to come down this way. Something like that. Okay. Let's clear these. Okay, now let me get back to the definition before I go to the examples. This y equal log of x to base a, this is called your logarithmic form. And this other part, x equal a to the y, that's the exponential form. Okay, so here you go from here to here by saying that x has to equal to this base taken to that power. There you go. And then you go backwards to get the other form. Okay. So the first example says write the exponential as a logarithmic expression. Okay, so it's an exponential, so I want it as a log expression. So I want the log. Okay, and I want this to equal. Okay, so from this, okay, you can see 5 to the x, 5 is the base, so that has to go here. And the x is the exponent, so that has to be the logarithm, so that has to go over here on this side. And then the 7 then is the value that goes here in the definition. So basically what we're saying is this value right here has to equal to this base taken to that power. So if I do that, I get the exponential. Okay. Now on the other one, next one, I'm doing just the opposite. So I have, let me clear this one. So this one says, rewrite the logarithmic expression as an exponential expression. Okay. So there's your log. So to go to exponential, I simply have to take the value, which in this case is x, the value in here, and that has to equal to whatever the base is, which is 2, taken to the value over here. In other words, the 5 is the logarithm, so that's the exponent. That's going to be here. X is equal to 2 to the 5th. That's your exponential. So log form is here, then we'll go to exponential. Okay, in the next examples, I'm simply using the definition of log. Okay, I'm not going to use your calculator here. Remember, the calculator you can use, you can find the answer if the base is 10 or e. Okay, here I have different bases. This one I can do in the calculator, but again, these are examples where I'm going to get the exact answer. So normally if they ask you to find the exact value, that basically tells you won't need a calculator. Okay, so log of 49 to base 7 is equal to what number? Okay, so basically we're saying, or asking, 7 to what power is 49? Well, 7 to the second is 49, so this should be 2. Okay, this is equal to log of 1 over 125 to base 5 equals to what number? So basically again we're asking 5 to what power is 1 over 125? Well, let me write the 1 over 125 in a different form so you can get a bit different perspective. So 1 over 125 is the same thing as 5 to the negative 3 power. Okay, 5 to the third is 5 times 5 times 5 times 5, which is 125. So 5 to the negative 3 is 1 over 125. Okay, so now let's just look at this expression. Log of 5 to the negative 3 to base 5 is equal to what number? Okay, so basically again we're asking 5 to what power is 5 to the negative 3? Well, it has to be negative 3. 5 to the negative 3. That's equal to 1 over 125. That's your answer. Okay, in the same way, the next one asking log of e, the natural log of e to the 4th is equal to what value? Remember, the natural log has base e, so this is e right here. It's understood. They don't put it in there, but it's e. So this one's basically asking e to what power is e to the 4th? Well, again, pretty straightforward. That's 4. Okay, so that's the way you would handle those where they ask you the exact value. Okay, now let's look at these. These are logarithmic equations. Again, in the last lesson we looked at exponential equations, those are just equations that had one or more exponentials. logarithmic equations are simply equations that have one or more logarithmic expressions. Okay, so let's look at this one. It's natural log of e to the 2x is equal to 10. I want to solve for x. So remember the base here is e. So I can rewrite the left side as 2x. It simplifies. Because the base is e, the log of e to the 2x to base e is 2x because e to the 2x is e to the 2x. Just by definition of log. So this simply simplifies to 2x equal 10. Divide both sides by 2. And we get x equal to 5. X equal 5. Okay. 2x equal 10. Divide both sides by 2. We get x is equal to 5. Okay, the next one, we have the log of x minus 2 to base 4 is equal to 2. We want to solve for x. So again, what I'm going to do here is I'm going to rewrite this one, because in this case I can't simplify the left side like I did over here. Okay, it's a different type of problem. I'm going to write it in the exponential form. So in exponential form, using the definition, this would just mean that x minus 2 would have to equal to 4 to the 2. Okay, definition. This value here, whatever this is, whether it's x or x minus 2 or x squared plus 5 or whatever, this expression here has to equal to this base, 4, taken to whatever you have over here. That's your logarithm. So 4 to the second, this is, well, yeah, okay, I was going to write it as 4 to the second. Okay, but this is just 16. So we add 2 to both sides and we get x is equal to 18. Okay. Now in a later section we'll go into more detail. Solving logarithmic equations will be a little bit more complicated than these here. But in this case, these are pretty basic. That's the way you would solve them. Clear? Okay, now let's look at these here. We talked about the domain of the standard log function. Okay, so here I want the domain. So this will say it's f of x is equal to log of 2x minus 1. What is the domain? Well, remember, you can only take the log of a positive number, so that means that 2x minus 1. If we want to find the domain of this, we know that 2x minus 1 has to be positive. This has to be greater than 0. So the domain will simply be the solution to this inequality. So this would be 2x would be greater than 1. Add 1 to both sides. Divide by 2. X would have to be greater than 1/2. Okay. So notice if I put 1/2 right here, I get 1 minus 1 is 0. The log of 0 is not defined. If you take your calculator and hit the log function, log function, enter 0, enter a negative number, and hit enter, your calculator will give you an error. Okay, because the log of a negative or the log of 0 is not defined. So for this particular one, then for this expression to be positive, x would have to be greater than 1/2. Okay, so here's the solution written in interval notation. Okay, now next one, pretty much the same sort of thing. I want to know, define the domain. X plus 1 over x minus 2 would have to be greater than 0. Okay, x plus 1 over x minus 2 would have to be greater than 0. So I would have to solve this inequality, kind of like the ones we did in an earlier section. Okay, so this is where we're solving rational inequalities, and we took the zeros of the numerator and the zeros of the denominators. Okay, so the numerator is 0 at -1, so I plot -1 here. And the denominator is 0 at 2. And then I simply plot these on the number line, and then determine the sign of this rational expression over these intervals. Okay, so -infinity is here, plus infinity is to the right of the 2. Okay, so let's pick a number larger than 2, say 3, and put it in where the x is. Everything's positive. If I pick a number between -1 and 2, say 0, okay, put it over here, I get 1 over -2. That's negative. Okay, so in between, if you pick numbers between -1 and 2, this expression is negative. If I pick a number less than -1, say -2, okay, put a -2 where the x is, a -2 where the x is down here, I'll get a negative over negative. That's positive. Okay, so since I'm dealing with a log function, I simply want only values that make this expression positive, and those would be numbers to the right of 2 or numbers to the left of -1. Okay, so you would write it like this. Okay, so -infinity to -1, union 2 to infinity. Okay, that's your domain. Okay, clear this. Okay, sketch the graph of these. So just a little rough sketch of the graph. So I want the graph of the log of x plus 3. Okay, so here I'm going to apply the same ideas that I went over when I went over the graphing of exponential functions. So this is base 10 here. Remember, it's understood. So base 10 would tell me that the graph would pass through 1, okay, and it would go like this, go out like this, something like this. That's if it didn't have this plus 3 here. That would just be the graph of f of x equal log of x. But because I had this x plus 3, this actually moves it to the left 3 units, because notice x plus 3 would have to be greater than 0 for this to be defined. That would mean that x would have to be to the right of -3. So what's going to happen here is that I'm going to have, instead of having a vertical asymptote at x equals 0, it's going to shift over here. To x equal -3. Okay, so it's this line here. Okay. Everything moves over 3 units to the left. So instead of passing through this point here, 1, 0, move over 3. So 1, 2, it's going to pass to this point right here. And that would be the point -2 and 0. So the graph then is going to go up through that point and come out something like that. Okay, and this is just a rough approximation because of this 2 that I have here. But that's the way the graph is going to go. And you can kind of verify, you know, this is the point -2, 0. So if I put a -2 here where the x is, I get -2 and 3 is 1. And the log of 1 to base 10 is 0, because 10 to the 0 is 1. So that tells me that's what the graph looks like. Okay. And we clear this. The next one, again, this is natural log, so ignore this -3 and ignore the -2 for now. But this is base e, and e is approximately 2 point something. Okay, so it's a number larger than 2. So the base then is larger than 1, so it's going to have the same shape as the one I just did, but it's going to be in a different position. So here's a situation ordinarily the graph would pass through this point right here, 1, 0, and then the vertical asymptote would be the y-axis, and the graph would go like that. Okay, but the x minus 2 shifts it over to units. Okay, so if I didn't have this minus 3, the graph would pass to this point right there, and that would be the point 3, 0. You can check it. 3 minus 2 is 1. The log of 1 to base e is 0. Okay, so if I didn't have the minus 3, the graph would go like this and approach the x-axis. Okay, now what the minus 3 does, it moves it down 3 units. Okay, so let me just go 1, 2, 3. Okay, so instead of this point being there, it's going to go here, and it's going to go something like this. And it's just going to go up. Okay, and of course you can check that out on your graphing calculator. Okay, in the next lesson, I'm going to look over some properties of logarithms, which will be very useful in solving more complicated log equations. So please subscribe to the channel, and we'll see you next time.